Alright, let's do a difference of cubes. If it's the first time you ever see this, let me give you some pointers here to try to spot them. Here you just have the difference, x minus y, and on the other side you have a bunch of x's and y's, but there's a certain pattern to the madness here. Look at the number of x's. You have 2 x's first, and then 1 x, and then no x's. So they decrease from 2 to 1 to 0 on the number of x's. Look at the number of y's. You have 0, 1, 2. They increase the number of y's. So one of them is going down, the other one's going up. That's the perfect pattern for a difference of cubes. So again, if you're a beginner and you've never done this before, you might try doing it something like a kindergarten method. How about this? X squared plus xy plus y squared times x plus negative y. Let's do some kg on this baby. That one would give you negative y to the third. That one would give you xy squared with a negative. This one would give you x squared y with a negative. That's these two. And I'm done with that. Now I go with the x's. That was that one times that one, that one times that one, that one times that one. Right? Now I do the x's. I'm going to do x times that, x times that, x times that. So x times that would give you x y squared. X times that would give you x squared y. X times that would give you x to the third. And now I add them. So I would get x to the third. These two are opposites of each other, so they give you 0. These two are opposites because they give you 0, so they give you 0. And all you're left with is the difference of cubes. I told you. So here's something famous for you. Every time you have a cubed minus another cube, the difference of cubes, you should think that's the multiplication of a famous couple of polynomials. The number of x squared, x's decrease, the number of y's increase. Just like that. Famous, famous, famous difference of cubes. Okay. Not only that, but you could extend this difference of anything. If I had x to the 5 minus y to the 5, you could play the same game. This would be x minus y, and then the number of x's decrease, starting with 4, 3, 2, 1, and no x's, and the number of y's would increase. No y's, 1 y, 2 y's, 3 y's, 4 y's. Right? So you can't see that. Too bad. You gotta pay extra if you want to see that. Alright, anyways, no, I'll do it here. Let me think. Yeah, I'll do the one for 4 right here. X to the 4th minus y to the 4th. First you do x minus y, and then you put the rest of it here. 3 x's, 2 x's, 1 x, and no x's. Number of y's, no y's, 1 y, 2 y's, and 3 y's. And that's how you do it. These are super famous. Again, if you want to see why, you should try the kindergarten method like we did here. And so you should put that in your brain somewhere where you have a drawer for all the famous stuff, for all the famous polynomials. A drawer in your brain. So then let me think. So then problems may look something like this. Here, check the pattern here. You got this guy squared, that guy square. The number of triangles decreases, the number of squares increases, and you have the difference over here. That's a perfect candidate. That is triangle cubed minus square cubed by difference of cubes. And you're done. Or you could do it the long way if you want. Pretty nice, huh? Same thing here. 2x, the quantity squared. The number of 2x's decreases, the number of 1's increase, and you have the difference over here. So this would be 2x to the third minus 1 to the third by difference of cubes. And you could simplify that if you want. 2x times 2x times 2x. That would be that if you want to be a pattern hider. This doesn't hide the patterns, this hides the pattern. Difference of cubes, easy. By the way, I want to show you something interesting. What would happen, this is true for no matter what triangle is. Triangle could be anything, blah. This one could be some other thing. Some other thing. Anything would work here. Well, as long as it's part of the real numbers, things that our axioms apply to, then you could, everything, the whole world is open. Anything where our axioms apply, you could plug them in there. In particular, what would happen if I substitute triangle is equal to x, and I substitute square is equal to 1. If it's true for everything, it's certainly true when this is the case. So if I substitute that, I would get that x minus 1. What I'm doing here is everywhere I see a triangle, I would substitute an x. And everywhere I see a square, I will substitute a 1. So this will be x squared plus x times 1 plus 1 squared. This will be a certain case of the difference of cubes. But wait, this becomes x minus 1 times x squared plus x plus 1. And this becomes another super famous. This is called the geometric polynomial number 3. This guy is equal to x to the third minus 1 to the third, of course, which is x to the third minus 1. Because I knew that this one was equal to the triangle to the cubed minus square to the cube, so I substitute x to the cube is that, and what the square to the cube is that. This becomes something famous, and so every time you have, for example, something like this, x cubed minus 1, you should think, oh, that's x minus 1 times x squared plus x plus 1. And in disguise, what that is just a special case of the thing you already learned, the difference of cubes, where the first item is an x and the second item is a 1. And there's more to that. Just like there was the difference of fifth powers, there's also the x to the 5 minus 1. So that one would look something like this. X to the 5 minus 1. It would look like x minus 1. And then the number of x's decreases. 4, 3, 2, 1. And the number of 1's increase. But you don't even need to put the 1 there because 1 doesn't do anything. So all you have is a 1 at the end. 1 to the 4th if you want to be pedantic about it. Some nice stuff here happens, and this is a family of other super famous. This will be called geometric series polynomial number 5. This is number 3. This gives rise to another family of famous polynomials, which are really just those same ones in disguise. Okay, and the other thing I want to say, if you ever are stuck and you have no idea, you could just multiply it out yourself. If you don't know what x minus 1 times x squared plus x plus 1 is, well, then you can use kindergarten method and do it for yourself so that you own it, and you'll see what it is. Okay, some nice stuff here.